In this tutorial, we're going to look at aerological diagrams, or otherwise known as skew-T or log-P diagrams. We'll just call them aerological diagrams. And this will be helpful for your practical 5. Okay, so what is an aerological diagram? Well, this is an aerological diagram. It's quite complex. There's lots of lines. And why is it useful? Well, it's useful because it ties together everything we've learnt in the last lecture on atmospheric stability. It is, in fact, what the Bureau of Meteorology uses to determine whether or not the atmosphere is stable or unstable, and it's central to the forecasting of weather on a daily basis. It's also used by glider pilots to work out whether or not they will get uplift and hence keep themselves flying. But this is an example here of a real aerological diagram from the Bureau of Meteorology, taken from today, the 15th of September. Now, in addition to those lines in the background that we see of the diagram itself, plotted onto this diagram is the temperature profile of the atmosphere recorded from a weather balloon released by the Bureau. We're just going to be focusing on the lines on the right-hand side, the red and the blue lines there. The red line is today's temperature profile, and the blue line is yesterday's temperature profile. The two lines on the left, the much more squiggly lines, is the dew point profile, and we're not going to use those because they won't help us as much when determining whether or not the atmosphere is stable. So we're just going to use the temperature profile as recorded by the weather balloon. Alright, we'll come back to this diagram a bit later on and you'll see, well, hopefully it'll make a bit more sense. Alright, so we've had a look at our diagram. Now let's remove all of those lines and start with a blank page. And I'm going to put on to this blank page each of those lines one by one so that you can see what each of them is doing. And then we'll put it all together at the end and plot some temperature, some atmospheric and air parcel temperatures to work out whether or not we have a stable or unstable atmosphere. Alright, so the first line is this line, these lines here, and these lines show elevation. It's not actually elevation, it's a surrogate for elevation. It's air pressure. It's better because then the ideal gas equation applies, PV equals RT, and the diagram then that can be used for all places on the Earth's surface, irrespective of starting elevation, because we can have different air pressures and plot those air pressures onto this standard diagram. But we can just think of it as being a surrogate for elevation through the atmosphere. So at the bottom there, we have 1,000 hectopascals at sea level. As we rise with elevation, the air pressure decreases because there's less air above us. Did you know that 1 cubic metre, 1 metre by 1 metre by 1 metre of air, weighs about a kilogram? I didn't until I Googled it. There you go. So, you don't notice it, of course, but nonetheless, it weighs something, and a cubic metre is not actually that much. A cubic metre of water weighs 1,000 kilograms, but nonetheless, 1 kilogram of air takes up 1 cubic metre. Okay, so they're the first lines that we see on the diagram. Quite simple. The next line we're going to have a look at is how temperature changes with elevation. And as we have learnt, that temperature also changes with elevation, certainly in the troposphere. And as I've said before, on the whole, and we'll have a look at that aerological diagram, the real one, and see where it doesn't quite always fit, but on the whole, temperature decreases with elevation. Now, this set of lines here is fine if it was 40 degrees at ground level where you were standing. But it's not always 40 degrees on every place on the Earth. Of course it's not. And so in order to make the diagram useful, we have to skew the lines like this. Now we can use whatever temperature we actually have on the ground surface as measured by our weather balloon as we're holding it on the ground surface. Because if we take these lines and place the other set of lines at elevation, we can now see that it doesn't matter what our starting temperatures are, we can plot them anywhere along that sea level ground surface line down here at the bottom. Can you see that? So it could be 40 degrees, in which case we would start over here, but our starting temperature might be 20 degrees, and so we would start here. And so if it was 20 degrees as temperature as the weather balloon went up with elevation, we can also then see how the temperature changed as the weather balloon passes through that atmosphere. So at sea level, it's 20 degrees. Make sure you know how to read it, so you follow those temperature lines that we've skewed. Okay, so at sea level, we put a dot, and we've measured with our weather balloon that it's 20 degrees. Well, we can now read that. Now, if we went up through the atmosphere to about 725 hectopascals, or the equivalent elevation at our place on the Earth's surface, what is the temperature at 700, where the air pressure is 725 hectopascals, as that weather balloon is rising through the atmosphere? Well, by using those temperature lines, we can see that it would be 10 degrees. Okay, we raise the weather balloon a bit further, and we reach the elevation that is equivalent to 600 hectopascals. What's the temperature there? Well, the line needs to be drawn parallel to those other temperature lines. And then you have to think, well, what is that? Well, it's 3 degrees. How did you work that out? Because you, in your head, just drew 10 lines between 0 and 10, and then matched up your line to one of those temperature lines. And so it's 3 degrees. Okay, see how that worked? So we've looked at elevation, or air pressure, and now temperature. Okay, let's get rid of those. Start with our blank page again. The next set of lines we're going to look at are these curved ones. What are these? Well, these lines show how a dry parcel of air changes its temperature if it is raised. Okay, so we talked about it in the lecture. If you haven't seen the lecture, make sure you have a look at the lecture before you look at this tutorial, because it will make much more sense. Alright, so these lines show how the temperature of an air parcel will change as long as it is dry. So let's put on our elevation lines, let's put on our temperature lines, and have a look at what happens. Let's say we're standing out on the land surface with our weather balloon, and we've measured the temperature at 20 degrees. Okay, so it's 20 degrees. As that air parcel rises, the temperature of the air parcel will follow the nearest, parallel to the nearest line. Okay? So, as that air parcel got to, about 890 hectopascals, what would the temperature of the air parcel be? PV equals RT, but you don't need to use that formula. We can use this thermodynamic or skew T log P diagram. And the temperature would be, can you work it out? It would be 10 degrees. If that air parcel was forced up and continued to rise and it got to 700 hectopascals, what would the temperature be? It would be somewhere between 0 and -10. Try and focus in on the lines that you're interested in. And the temperature would be -8. All right? Go back to our blank page. The next set of lines are these lines. What on earth are these lines? These lines show the temperature of an air parcel as it rises through the atmosphere after it has become wet. So after it's reached its dew point temperature. Remember I said that the rate of change, the saturated adiabatic lapse rate, is less, and so these lines are more vertical than those dry adiabatic lapse rates. Okay, let's put on the other lines, our elevation or pressure lines, our temperature lines, and we can superimpose our dry adiabats over the top. And let's have a look at what happens to an air parcel at 20 degrees. Starting point is 20 degrees. As it rises, in this example, it gets to about 710 hectopascals. Because of the amount of moisture in the air parcel, it turns into a cloud, and then it must follow parallel to the nearest wet adiabat. Now I've drawn those two lines actually on the dry adiabatic line and the saturated adiabatic line, the wet adiabatic line. But your starting point could be anywhere. It could be 21 degrees, could be 25, could be 30. And so you would need to draw your change in temperature parallel to the nearest lines, the saturated or the dry adiabats. All right, blank page again. These last lines are known as the humidity mixing ratio, or otherwise just simply our humidity lines. So they show the grams of moisture in each kilogram of air. Okay, remember, we can also measure that with our weather balloon. These lines go in all different directions, so as I said, you need to focus in on the lines that you're interested in. All right, so let's have a look at these. So let's put on our elevation lines, our temperature lines, and this time, before we put the other lines on, here we have our air parcel, and its starting temperature is about 32 degrees. What's the maximum amount of moisture that that air parcel can hold? Now we could look it up with a table, but we can also read it just off this diagram. The maximum amount of moisture that air parcel can hold at 32 degrees, right? 32 degrees is, you follow then the humidity mixing ratio line, and the answer is 30 grams per kilogram. Now, the actual amount of moisture in the air has been measured by the weather balloon, and we've measured it at 7.5 grams per kilogram of air. Now I've stuck it up on the right hand side of that diagram, and you'll see why in a minute. But knowing those two data points, we can now work out the relative humidity, as we saw in the lecture. And so if we know that the maximum amount of moisture the air can carry is 30 grams per kilogram, the actual amount of moisture in the air is 7.5 grams per kilogram. What would the humidity be? Well, it would be 7.5 divided by 30 times 100. So it's 25% relative humidity. Okay, that's good. What we can then do is add a line parallel to the humidity mixing ratio lines that shows 7.5 grams per kilogram. Now, why is that useful? Because when the maximum amount of moisture in the air that the air can carry equals the actual amount of moisture in the air, what does that give us? That gives us a relative humidity of 100%, we have saturation, and we have a cloud forming. So let's have a look at that in practice. That is our dew point line. So let's start off with an air parcel at 32 degrees. Remember, 32 degrees, we can read that off our temperature lines. And put on our dry adiabats and our saturated adiabats. And let's see what happens to an air parcel at 32 degrees. Well, that's a good starting point, but we also need to know what our dew point line is. So we've measured, remember, again, we've measured the air humidity at 7.5 grams per kilogram. We can draw a line that represents 7.5 grams per kilogram. And then we can start to raise that air parcel and cool it as it rises. So what happens? It needs to follow the dry adiabat until what? Until it reaches that humidity mixing ratio line that represents, in this case, 7.5 grams. Why? Because the maximum amount of moisture that that air parcel can now carry is only 7.5 grams because it's cooled to that line. You see how it works? So now the actual amount of moisture in the air parcel equals the maximum amount of moisture in the air parcel. And so what do we get? We get a cloud. And so how does the air parcel cool then if it is still forced to rise? Well, it needs to follow parallel to the nearest saturated or wet adiabat, and there's the line there. So that now represents the temperature of that air parcel as it rises through the atmosphere, as long as it is still forced to rise. So it could be by any one of those three processes. Okay, good. Let's keep going. Let's now have a look at what can happen in reality. Now, here we have a point on the Earth's surface at 1,000 hectopascals, or at sea level. Now, we're going to call that the temperature of our air parcel at ground level. Here, we have our dew point of this air parcel. So the relative humidity at sea level can be calculated if we know the maximum amount of moisture that the air can carry and the actual amount of moisture that the air has. So we can determine the maximum amount by taking our air temperature that we've measured with our weather balloon, and we have there 26 grams of moisture per kilogram of air. That's the maximum amount of moisture that air can hold at sea level. The actual amount, as we've measured with our weather balloon, is 13 grams of moisture per kilogram. So the relative humidity is 13 divided by 26 times 100. So we have relative humidity of 50%. Okay, that's good. Now, let's remove that. Now let's have a look at, we're going to not focus on our air parcel, we're going to actually focus on just the atmosphere. So we have our weather balloon, and we're going to release that weather balloon and take readings every 500 or so hectopascals. We'll just take it through the atmosphere with elevation. Each time it's taking a reading until we get up to the top, and we get rid of our weather balloon, and we have a look at the temperature profile. And we can plot that on the graph. And so at 1,000 hectopascals at sea level, it's 29 degrees, and then it progressively decreases. It jumps around a little bit, but in this case, it progressively decreases. And we can plot that on our graph, on our thermodynamic diagram. Okay, so each of those points, we take its elevation and we find its particular temperature, and that gives us the point that we can plot on the graph. We call this the environmental lapse rate, which we've seen before. So that's the temperatures of the surrounding atmosphere as measured by the weather balloon. Right, and then we can draw a line joining those dots. Okay, now moving on, let's get rid of those lines and let's have a look at what happens when the air parcel rises. So we know when 100% humidity is reached because it'll be when the air parcel rises and intersects with our dew point line. So let's raise an air parcel from ground level. Well, that from ground level, it's the same temperature as the first measurement of the weather balloon, and it rises following that dry adiabat until it intersects our dew point line. What happens there? We get a cloud. It's now saturated and so must follow parallel to the wet adiabats. And there we go. And what do we see? We can see that it has intersected with the environmental lapse rate. Remember what that means? Removing those text boxes. The lifting condensation level of the parcel of air is the intersection of the dew point and humidity mixing ratio lines. So the lifting condensation level is where our cloud has formed, and in this case it's approximately 845 hectopascals. You can read that off the graph. At that elevation, the parcel now follows the wet adiabat, and the level of free convection then is the point where the wet adiabat intersects the environmental lapse rate. And why? Because just above that intersection now our air parcel is warmer than the surrounding atmosphere and will then rise by itself. So as I said in the lecture, if the force that is causing it to rise is allowed to continue, such as air going over a mountain, as long as it is still being pushed up and it gets to that elevation that is the same as the level of free convection, then the mountain or the force can disappear and it will now rise by itself. All right. And that's that point there. So, is the atmosphere at that location on the Earth's surface stable or unstable? Well, it's neither, because we call that conditionally unstable. And what's the condition? It needs to get to that level of free convection, the elevation that is equivalent to that level of free convection point, in order for it to be unstable. So it's stable at all elevations below the level of free convection, and it is unstable at all elevations above that level of free convection. Now, if we have a look at, go back to our aerological diagram from September the 15th, then we can zoom in to the area of interest. Remember I said we're going to just look at the temperature lines. The pattern of temperature for the 15th and the 14th is similar, so that's good. And we can see there, if we just follow the red line, that's our environmental lapse rate. Okay, and we can have a look at the path of the air parcel, how it changes in temperature. And so as the air parcel rises following the dry adiabat, you can see that it reaches its lifting condensation level at around about, looking at it, what's that, 920 hectopascals. And from that point, it then follows the wet adiabat. Now, what's interesting, just because this is real data, that just happens to be, just coincidentally, also the level of free convection. So, just coincidentally, as that air parcel rises, it reaches its level of free convection and its lifting condensation level at approximately the same elevation. So that air parcel is now free to rise and form a cloud, until it gets to where, looking closely at that diagram, you'll see that the temperature of the surrounding atmosphere intersects again with the temperature of the air parcel as shown by the wet adiabat. And where does that occur? Looking closely, it's around about 710 hectopascals. Above that elevation, the surrounding atmosphere is again warmer than that air parcel would be. So what does that say? Well, it can no longer continue to rise. It would become, because it's cooler than the surrounding atmosphere, it would become stable. And so it would start to sink. It can't sink all the way down below 920 hectopascals, because then it would be warmer. And so what do we have? So we have cloud development between 920 and about 710 hectopascals. So not huge cumulonimbus forming, which would go right through the atmosphere. For that to happen, the air parcel temperature would have to be warmer at all elevations from its level of free convection. But in this case, it's not. So the cloud cover is restricted between two elevations. And if you have a look at the forecast for Brisbane, you'll see that it's partly cloudy. And that kind of makes sense. You'll have clouds forming, but not huge extensive cloud cover. There's more to it, more to the forecast than just looking at this aerological diagram. But you can see how it starts to fit, and having an understanding of these processes allows you to start to link together, again, what's going on up in the atmosphere. All right, so I hope that's given you a bit more understanding, and certainly hope it'll help you with Practical 5.